Hello everyone, my name is Thomas, and today my group and I will be presenting on the uncertainty principle. So the uncertainty principle was devised by this man here, Werner Heisenberg. Werner Heisenberg was a German physicist and is considered one of the key players in the development of the field of quantum mechanics. He first came up with the idea of the uncertainty principle in 1927, and he would later go on to win a Nobel Prize in 1932 for his contributions to the field. So the uncertainty principle states that it is impossible to know both the exact position and the exact momentum of a particle at the same time. So here's our equation for the uncertainty principle. We have delta x being our uncertainty in position, delta p being our uncertainty in momentum, and then we have h bar over 2 on the other side of the inequality. H bar is equal to h over 2 pi, with h being Planck's constant, so I'm sure you are all very familiar with that now. And here's a more of a visual representation of how this equation plays out. So as you increase your uncertainty in x, your uncertainty in momentum decreases. And we can see that visually on the far right of the slide with the position of that dot being a little more ambiguous, but the momentum of it being very straightforward. And then below that, we can see that as we decrease our uncertainty in x, our certainty in p increases. And we kind of have the opposite on the far right of the slide, where our dot is very easy to tell where it is, but our momentum is more vague.
All right, so my name is Anna, and now that Thomas has introduced the uncertainty principle, I'm going to show you one way in which we can see this principle in action. You've probably heard of the double slit experiment before because it's pretty famous for demonstrating the concept of particle-wave duality, but it's also a really great example of how decreasing uncertainty in position will increase uncertainty in momentum, and vice versa. So here's a PhET simulation of the double slit experiment. I'm going to be using photons for this, but other particles are applicable as well. With no detectors on, we can go ahead and send those particles through the slits, and we can see that this really nice interference pattern forms. This is because the particles are acting as waves in this moment. But if we reset this and we add a detector to either slit or both, we can go ahead and send them through again, and we can see that this interference pattern goes away. So why does this happen? Well, this is because we can't know position and momentum at the same time. When we add the detector, we are decreasing the uncertainty in our position, and in turn, we lose information about the momentum. But on the other hand, when there is no detector, there's a lot of uncertainty in our position, and we don't know which slit the particle is going through. But there is more certainty in the momentum, which is why we can see this consistent interference pattern form. So now that you've seen a visual explanation of how the uncertainty principle works, hopefully you'll be able to apply this concept to other situations as well.
Well, let's get started with our first example of this principle. To start off with, we are going to work with something easy to visualize since it is much larger than an electron and most everyone has some experience with it, a baseball. Let's say some random guy, who we will call Dwayne The Rock Johnson, throws a 20-gram baseball. Baseballs are easy to see, so we know the position of the baseball with an uncertainty, or delta x, of 5.0 times 10 to the negative 32 meters. We want to know the uncertainty in the baseball's velocity. Unsurprisingly, we use the equation for the uncertainty principle that was previously covered. We are solving for delta p, the uncertainty in the momentum. So we fill in 6.626 times 10 to the negative 34 joules per second for h, and 5.0 times 10 to the negative 32 meters for delta x. Obviously, 4 and pi are constant, so they're always the same. We will then solve the filled-in formula by dividing h by 4, and then pi, and then the uncertainty in position, giving us an intermediate answer of 0.0011 kilogram meters per second. This is not yet our final answer, as we need to account for the mass of the object in order to convert this to uncertainty in velocity. We will divide the initial answer of 0.011 kilogram meters per second by the 20 gram mass, and we will get a resulting answer of 0.05 meters per second for the uncertainty in velocity. That is our final answer. Most important thing is to make sure you remember to divide delta p, the intermediate answer, by the mass to get that uncertainty in velocity. Sometimes we will be given the uncertainty in velocity instead of the uncertainty in position. So let's see how that, along with focusing on something much smaller than a baseball, changes things in our next example.
So now that we've practiced using the uncertainty principle for something large like the rock throwing a ball, let's look at something a little bit smaller like electrons. In the most basic depictions, like the Bohr model shown here, we see electrons orbiting the nucleus in a perfect circle. But we know that that depiction is not really accurate. So now we draw them in orbitals, like this. But why do we depict them as orbitals? Well, it's because we can't know the exact position and momentum of an electron at the same time. An even more accurate depiction of orbitals even looks kind of more like this. This represents the probability of finding an electron in a specific region. The uncertainty principle is one of the reasons that we depict electrons as probability densities. So now let's apply this information to a practice problem. For a hydrogen atom, the uncertainty and velocity of an electron is measured to be roughly 5.78 times 10 to the 5th meters per second. The mass of an electron is 9.109 times 10 to the negative 31st kilograms. What is the uncertainty in position? So here are some helpful equations, constants, and values on the right. And before I get into solving this problem, you are welcome to pause the video and take a minute to try it for yourself. So first, we have to plug in h over 2 pi for h bar. Then we can substitute in m times delta v for our momentum. Now we simply rearrange the equation to solve for our delta x, and we can plug in our values and just solve it. So the answer that you should have gotten for our uncertainty in position should be 1.00 times 10 to the negative 10th meters. This value is roughly the diameter of a hydrogen atom. This makes sense in the context of atomic orbitals because we don't know the exact position, but the uncertainty principle can help calculate the probability of where it might be. So now that we've explored how the uncertainty principle is applied to position and momentum at an atomic level, we can now look into some other applications of this concept.
So when we apply the uncertainty principle to energy and time, we see that the more precisely we know the energy of a particle or of a system, the less precisely we can know how long it stays in that energy state and vice versa. If a molecule stays in an excited state for only a short time, delta T is going to be small. Then there is greater uncertainty in its energy, so delta E will be large. This is why very short-lived excited states like fluorescence or chemical intermediates have broad energy bands in spectroscopy. So for the uncertainty principle, we see that delta T times delta E is greater than or equal to h bar over 2. We see that delta E is the uncertainty in energy, delta T is the uncertainty in time, and then h bar is the reduced Planck's constant. So it's going to be h over 2 pi. The uncertainty of the energy for an excited atom is roughly 2.7 times 10 to the negative 26 joules. What is the uncertainty in time? Using some simple algebra, we will manipulate the equation to get delta T is greater than or equal to h over 4 pi delta E, in which we will plug in 6.626 times 10 to the negative 34th joules per second for the Planck's constant, which is going to be h, and the uncertainty energy will be 2.7 7 times 10 to the negative 26 joules, and then that's going to be plugged in for delta E. So after calculating, we will see that delta T is greater than or equal to 2.0 times 10 to the negative 9th seconds. So the uncertainty principle in relation to energy and time essentially tells us that there's a trade-off. We can't pinpoint exactly how much energy something has and exactly how long it has it. So in physical chemistry, this explains why things like broad absorption peaks and short-lived excited states.
Let's go over what we have learned throughout this video. We learned of Heisenberg, a physicist from the early to mid-1900s, and the man who created the uncertainty principle we have discussed in this video. We learned that the mathematical formula for that principle is delta x times delta p equals h bar over 2. We also talked about the double slit experiment, which can be used to experimentally show the relationship between the uncertainty of position and uncertainty of momentum when attempting to observe things at an atomic level. As the size of the slits are adjusted, the uncertainty in position decreases, but at the same time, the ability to determine the velocity of the particle increases. We also covered some practice problems to show how to apply the uncertainty principle mathematically for varying unknowns. It was easy to understand that for a big, easily visible object, like a baseball, the uncertainty in position would be quite small, and we calculated and found a large uncertainty in momentum and velocity. This helps show the inverse relationship between the two uncertainties. In our second practice problem, we highlighted how understanding the uncertainty principle can be related back to atomic orbitals and the probability of an electron's location within an orbital. Finally, we extended the uncertainty principle from position and momentum to time and energy. Just like our normal uncertainty principle formula, time and energy have that inverse relationship equivalent to h bar over 2. To wrap it up, when we get into the observation of things on such a small scale as electrons, classical physics breaks down and we get an uncertainty principle as a result.